I'm going to show to you a problem walkthrough, basically, of some of the problem sets I gave you. Remember the highlighted ones or the one box in red are the items that you have to answer for yourself. The instructions have been laid out in your Canvas site, and feel free to relay your questions if you have any. Chat group to your class representatives, or you just email me directly or ping me in chats. So hopefully this problem set walkthrough will help you in answering the problem set that you should be answering. Okay, and this is a pre-recorded session, and feel free to watch this all through with the PDFs I gave you, so that it may assist you in terms of solving the problem, analyzing how the problem and the solution that we implement. Okay, so just a walkthrough. So these are the problems as I gave you. So and I thought about giving it a category like moment about a specified access, so that you can see the difference. And also I added the answer already, so that you have a leeway. You have an idea of what the answer would be. Okay. 4-17 seems very familiar with our sample problem. The only difference is that we're rotated the AB axis. This one, it's kind of familiar because I think I gave 2 sample problems. It's also available in your book, and the steps are pretty clear. The challenge here is just choosing which position vector you want to rotate about. The next one is about moments. So here we're already given the magnitudes of the moments, 3 of them. It does look intimidating, but trust me, you've already encountered similar problem in lectures 2 and 3 before. Actually, lectures 2 to be specific. And then this one is a lot simpler because you're given 2 couple moments detail, and all you have to do is just determine the magnitude. It's a different kind of problem. I'm gonna walk you through it. Here you're gonna solve this. This one is simple. All you have to do is just apply the equivalent couple method. Then finally we have simplification forces and couple moments. I specifically gave this just so that when you encounter a similar problem, whether in your finals or in your board exam, you know what to do. So there we go. And then this one is classic exam, replacing the loading system, but in 3D. Okay. And this is I just gave you this because I think this should suffice, but the rest will be examples. Okay. So let's start first with F4-17. So the final answer should be around this range. Okay. The thing about with getting the moment about specified axis, if when you're given a 3D and when you're given a force vector of in Cartesian vector notation, you would expect that your moment is in Cartesian vector notation as well. But in this case, it's already been expressed here. It's specifically mentioned to express the final answer as a Cartesian vector. We're being asked determine a moment, of course, given the F vector is 50 I hat minus 40 j hat plus 20k. How should we go about this? Okay, let's start first with the given. Okay, power chords, don't forget about it. Okay, so if you would recall, you will be using this kind of formula here. So we'll be using this kind of formula. But bear in mind that this only captures the magnitude. Okay, this is the moment magnitude. Magnitude. And for you to get the moment in Cartesian vector rotation, you have to multiply it by unit vector AB. So we're being asked the moment that's gonna be rotating about axis AB. So this one. Okay. And from here, there are two possible UAVs is quite easy to acquire, since all we have to do is just get the coordinates of A, position vector A, minus position vector B minus position vector A, and we will get RAB, and its magnitude for later. And for force vector, we're already given the Cartesian vector notation. Of course, forget this one. There we go, which is this. So all we have to do now is to determine what will be the position vector that we'll be using to rotate about axis AB. And the good thing about this is we have two possible position vectors, RAC and RBC. Let me just remove that thing. There we go. Let me just remove this. Okay. So just imagine where they are. They're probably around here. See that? This is your RC, which is the coordinates for position RC is basically 4 I hat plus 2 K hat. No Y. This the coordinate is not on the Y axis. It only exists in the X and Z axis. Okay. And then for position B, here I wrote the entire thing. So basically here we have, it exists only in Y axis. So we only have 0 I hat plus 3 J hat plus 0 K hat. Okay. So if we're going to determine the position vectors for RAC, it should look like this. RAC is equals to RC position vector minus RA position vector. So in this case, 4 and RA here, this one is position A, so that's only 4 I hat, so 4 minus 4 is 0. And 0J, since they have no coordinates in the y-axis, and point A doesn't have a Z, so it only exists in the x-axis, so that's 2 minus 0, so that will be 2K. So that's 4 minus 4, 0. RAC will be 2K. And here for RBC, so that will be RC minus RB. So where RB here is just 3J hat, okay? So the expanded form of the equation would be 4 minus 0 plus 0 minus, since point C doesn't have a y coordinate, it's got to be 0 minus 3, that will be 3J hat, and then plus 2 minus 0 K hat. Since point B doesn't have a x and z coordinate, 0, 0 I hat, and then 0 K hat, which will yield you RBC into 4 I hat minus 3J hat plus 2 K hat. Okay? Okay, if you're wondering where I got those coordinates, it's just here. This one, it's RB, 0 I hat, 3 J hat, plus 0 K hat. And for A hat, that's, I think I already wrote this in advance. It's going to be on the next slide, but let me just erase this down. Just erase this. There we go. So let me go back to line. Okay, so the A hat naman is here. There we go. So 4 I hat plus 0 J hat plus 0 K. Hence, this is the equation that I used here. And how was I able to get positions RAC at RBC? Again, we can choose between the two possible position vectors. So it's up to us which one will be the easiest. So next up, we know UAB, since we already have the coordinates for A and B. All we have to do now is just get the RAB position vector divided by its magnitude. We know coordinates of A, we know coordinates of B, so it's gonna be RB minus RA. So that's gonna be 0 minus 4, 3 minus 0, and then 0 minus 0, which will yield you negative 4I hat plus 3J hat and 0K hat. And you just get the sums and squares of those. You will now have this one, negative 4 over 5 I hat. You can also, simplify them into its lesson. This one is a lot simpler now. Plus 3 over 5 J hat. Okay, or negative 0.8 I hat plus 0.6 J. And these are unitless, so no need for units here or brackets, basically. So the next step is just substituting these values to our equation here to get our moment and the magnitude of our moment here. Okay, so it will look like this. Right. So where's the other one? There we go, 50. So just like our cross product, but instead of ijk, you will be adding first the UAV values, the unit vector AV values, which is negative 0.8, and then plus 0.6. And since there's no k hat, so that's going to be 0. Next up is the position vector. I chose RAC because it has 0 I hat and 0 j hat, so it has the most number of zeros. So I think you can also use RBC, but you will be multiplying across these values for I hat minus 3j hat plus 2k hat. So I chose RAC because it has the most number of zeros. So a lot of the equation, a lot of the numbers here will cancel. It's a lot easier for me. Okay, so you will put the position vector here on the second row, 0, 0, 2. And then finally the force vector, 50 minus 40, then plus 20. And all you have to do now is just expand them, just like so. So negative 0.8, it's going to be 0 times 2 minus the product of 2 times negative 40, negative sign, 6. That was, so what do we have here? 0 times 2 times the product minus the product of 2 times 50, and then plus 0 is basically 0. Simplifying down, and this is 0, 0. You have negative 64 plus 60. And simplify that, you will have negative 4 pound force feet, or basically 4 pound force feet clockwise. But remember, our answer should be, according to the problem, it is required that our final answer should be expressed in Cartesian vector notation. It's easier. Since we already have UAV, all we have to do lang is multiply the moment magnitude here with unit vector UEV. So that's negative 4 times negative 0.8 I hat plus 0.6 j hat, which will give you 3.2 I hat minus 2.4 j hat. Right? So what are the possible challenges, dito? Possible challenges here is just choosing which is determining the proper position vector at which your force will rotate with. Okay, so yun yung kanyang distance in between the moment axis. Okay, and then the other one would be identify properly your unit vector AB. So pag sinabi UAB yan, RB minus RA, then just get the squares and the sum of the square root ng the squares of the sum and square root of for the magnitude RAB. Okay. Next. All right. So this one looks intimidating, but I trust you that you already encountered it. And remember, you can treat them like force vectors or like any other vectors, but in this case, they're expressed in magnitude now. Right now, we're being asked to determine the resultant couple moment acting on the pipe assembly. Okay. So we're given the magnitudes of moment 1, which is 450 pound force feet, moment 2 at 250 pound force feet, and M3 at 30 pound force feet. So for solution, I'll give you a clue. Recall solving vectors in 3D. And all you have to do then is just express them in its Cartesian vector notation to arrive with the final answer of negative 20 I hat minus 40 j hat plus 100 k hat. And recall this equation where MR, the resultant vector, is equals to the sums of the individual vector component. In this case, moment vectors. Okay, and also recall that for you to convert the magnitude of moment into its Cartesian vector notation, you have to identify its unit vector. Where unit vector is simply equals to the quotient of its position vector over its magnitude. Okay, so let's do it one by one. Let's try it with M1 first. So unit vector 1 is equals to position vector R1 divided by its magnitude R1. What is R1 by the way? We're given dimensions here. So that's gotta be negative 2 I hat plus 2 j hat and then plus 3.5 k hat divided by the square root of the sums of the squares of each x, y, z axis. There we go. Like so. Expand them further, you will get the unit vector 1 negative 0.444 I hat plus 0.444 j hat plus 0.778 k hat. Okay, and M1 is just the product of unit vector and its magnitude 450. And you will have negative 200 I hat plus 200 j hat plus 350 k hat on force P. Remember, this unit vector is unitless. Okay, and now that we tried it with moment 1, let's try it for moment 2 and moment 3. For moment 2, it's quite easy. It's already pointing downwards, so technically it's just 250 times negative 1k. And unit vector are either 1 and negative 1. And since this is along the z-axis mismo, it's just literally negative 1k lang. So negative 250k pound force feet. Okay? If you're wondering para saan nakuha rin yung negative 1, there's a bit of, right-hand rule na nangyari dito, but you can always assume that it's gonna be negative 1 along the axis naman dito, especially for z-axis. Okay? So M2 is just negative 250k pound force feet. For M3 naman, we're given only, there's no k hat, there's only I and j, so we have positive 1.5 I hat, negative 2 j hat, and from that is your R3 position vector over its magnitude. So you square root mo yung 1.5 squared plus negative 2 squared, and this will give you 100 I hat, 180 I hat minus 240 j hat on force feet. Just gonna check my OBS. Okay, it's still recording. Okay, and then from there, all you have to do is just align them up and solve them algebraically and to get the moment resultant. It is going to be negative 20 I hat minus 40 j hat plus 100 k on force feet. Okay, so that when you encounter a problem just like this, you would know how to solve it. Okay, as you can see, I didn't exactly draw enough diagrams dito kasi di naman siya kailangan unless I told you so. Okay. Okay, next up. Let me just edit this lang. F and solve algebraically. I think hindi ko siya na-animate. Anyway, this one is actually quite simple lang. Because I think I've given enough sample problems here to know what to do. But essentially, we're gonna apply here equivalent couple method to determine F dito. But this time around, we're not gonna find the moment. We're just gonna simply find the force couple dito. Okay? We're given already the moment of 1.5 kilonewton meter clockwise. So meaning it's negative 1.5 kilonewton meter if we're gonna plug it in the equation. So we're here to solve to find the magnitude of F. So we're gonna apply the equivalent couple method, and remember that the resultant moment is equal to the sum of its individual moments. So we have two couple moments here. So moment 1 and then moment 2. This is our couple moment here. This is a couple moment here. Okay. So essentially, that's going to be negative 1.5 kilonewton meter. That's our given resultant moment. Okay, which is already specified in the problem. Equals to, let's just say our 2 kilonewton here is our moment 1, and apply the equivalent couple method simultaneously. That's 2 kilonewtons, so that's going on the direction counterclockwise. So 2 times 0.3, that's equivalent couple method. You just multiply the entire thing. 2 times 0.3, that's kilonewton meter, and now minus force F, minus because it's going in the direction of in a clockwise direction. So okay, so minus F, minus force F kilonewtons times its perpendicular distance 0.9. Okay, so that's the couple equivalent couple method. If you're having can't remember how to solve it, you may refer back to the PDF that I gave you and to the uploaded video that I also attached in your Canvas site. Okay, and now all you have to do is isolate force F and solve algebraically, and which will give you this particular equation. So that's gonna be, so transpose 1.5 equals to F divided by 0.9 on both sides. So we have this equation, and your final answer here, meters will cancel out, which will leave you kilonewtons. Always remember to cancel new units, just so that you won't notice. So this one will kilonewtons. Make sure this will be combined together. Okay? So para maging kilonewton meter, just shortcut it, and your final answer should be around 2.33 kilonewtons. Okay, it's pretty exact. Okay, so that's for problem sets under a couple of moments. Let's try naman simplification of forces and okay. For simplification of forces and couple moments, there's just two requirements lang naman dito. One is finding the resultant moment. Finding the resultant moment. Two, finding the resultant force. And if it's in two-dimensional, you have to find also the theta, which determining the direction of the resultant force. But when you're dealing with 3D, when you're dealing with Cartesian vector rotation, you don't have to find theta anymore, which is a good news. And when you're dealing with forces in 3 dimensions, all you have to do now is just you can still apply the same rules in simplifying forces and couple moments in 2D, but you have to convert them in Cartesian vector rotation. Okay, so just like what I said during the lecture, during my pre-recorded lecture. So we're here to find the resultant force and also the resultant moment in Cartesian vector. That is acting at point O. Here we are. So again, theta is no need. Since the problem is in 3D, final answer is in Cartesian vector rotation. Okay. What else do we have? We also have a given moment already here. So let's just identify that. We have a couple moment here, about 75 Newton meter. We have F1 at 100 Newtons and F2 at 200 Newtons with the following dimensions as well. Okay. So the solution is ganun pa rin. Let's start with force summation. So force summation to identify our force resultant. We call our lesson, we call our lecture 2, the summation of the resultant force vector is a summation of individual force vector notation. So it's gonna be F1, F2 in their Cartesian vector notation. So all we have to do na lang is identify yung Cartesian vector notation of the magnitudes 100 newtons, F1, and then magnitude 200 newtons, F2. Luckily, we're given dimensions dito. So for F1, it's gonna be just 100J. Since it's acting on the y-axis. I forgot the negative here. F2 acts on more than two planes. There we go. So for F2, we still have to figure out its position vector, and fortunately, it's just acting on this particular plane lap. Acting on x. It's acting on negative x and acting on negative z. Hence, your position vector here would be negative 0.4 I hat minus 0.3 k hat. Just like so. And your F2 would be, there we go. All you have to do now is just add them together. And you would have, wait. Yeah, so I'm obviously wrong here. This is negative. Negative. So that's the first correction there. Try to update na lang yung okay? Okay. It's a good thing we're checking this again. So yeah, so that's supposed to be negative 100J since it's in the negative y-axis. Sinulat ko na nga, hindi ko anyway, that's negative 100J. So the answer should be just the sum of F1 and F2, which will give you negative 160 I hat minus 100J hat and then minus 120K hat. Okay? Next up is the moment summation, where the sum of the resultant moment vector is equal to the sums of individual moments here. In this particular case, we're already given one particular moment, so we have to identify the moments for M1 and M2. So let's start with M1 move. N1 rotating about 0.0, so we have the perpendicular distance of 0.3, which would give us negative 75. No, sorry. That's for later pala. So here is the moment couple here. So it's rotating about, says something about 75 Newton meter. It's along the negative x-axis, pointing already in the negative x-axis. So that should be negative 75 I hat. Essentially, it's 75 times negative 1 I hat, and will yield you negative 75 I hat per meter. For M1, okay, you gotta do a cross product here. So that's gonna be R1 times F1. So R1 here is simply just 0.3 K. It's positive, by the way, and 0, 0, since it doesn't have X and Y coordinates. So it only has this particular point, just 0.3. And then you have F1 at negative 100 J hat, that's 0, 0. Then expand them. So that will be cancelled out because they're going to be 0. And then you simplify. M1 is simply 30 I Newton meter. 30 I hat Newton meter. M2 is going to be R2 times F2. You already have your R2 here. You already got that. So that's basically it. R2, R1. So your R2 is essentially here. This is the R2 here. So that's gonna be, doesn't have an I hat, but it has a 0.5 J hat positive and positive 0.3 K hat. That's in the negative 160, 0, minus 120. Then you will have this one, expand and form, cancel all the zeros. The answer should be negative 100 I hat minus 48 J hat plus 80 K hat Newton meter. That's pretty much the final answer. Okay. And then step number 3 here is try to visualize where it's gonna be. I think that's gonna be, it's not mentioned here, but I would like to ask you how to draw it. To draw it, to visualize it, all you have to do is just build your X and Y coordinates, just lay them in as such. You don't have to draw the entire thing here, but just mention this is point O, okay? So in this case, just imagine where it is. Okay, that's point O, and then you just have to follow the coordinates. So you don't have, it doesn't have to be that very precise. For example, for movement, somewhere here, since negative 105 I hat, so it's going to go here on the negative x-axis. Negative 48 j hat's going down on the negative y-axis, and then it's going to go up since it's positive 80 k hat. For force resultant, again, negative 160, positive 100 j since it's positive y-axis, and then negative 120 k hat's going down, just like so. Okay. So for this one, this is another problem of simplification of forces and couple movements. And here we're being asked to replace the loading shown by an equivalent single resultant force and specify the x and y coordinate. Okay, so all we have to do first is, find the resultant force and their corresponding x and y coordinates. So we're being asked, okay, where the resultant force is being applied at. What is the coordinates of the resultant? Okay, so the solution here, of course, is force summation. And force resultant, you need to find the FRX and FRY, square them, get the sums, and then get the square root as well. Just like so. Okay. And then from here, we have no horizontal. We don't have any horizontal forces, only vertical. So the summation of Fy, 100 minus 400 minus 500 newtons will yield you negative 800 newtons. And to get the square root of that, so f of x is 0. I'll be substituting the equation. So negative 800 squared plus 0 squared is square root that, and that will be 800 newtons. Okay. And then next up is the summation of moments, MR. And then just like in our previous, in our part 1, the summation of resultant movement can be solved by getting the by components. So mx plus my. So again, we can get the moments here about we can get the moments here about an axis. So in this case, we're going to get the moment about x and moment about y-axis to get our x and y coordinates in its line of. mmx is basically the summation of all the forces times its perpendicular distance, which is the y. So we're rotating about the x-axis. So our perpendicular distances is our distance y relative to our rotating axis. Y here is known, okay? And we already got our FR here, since the force resultant is basically the total force times y, and y is the perpendicular distance. But we do know the individual forces here. So our moment of x is also equal to FR times y, which is also equal to the summation of all the forces and their respective perpendicular distance. Here, let me write it. Like so. Okay, in this case, 100 here is acting along the axis of rotation. That's gotta be 0, so there's no moment. Here we have 400 newtons here. It's rotating clockwise, so that's negative 400 times perpendicular distance times 4. We have another one, 500 rotating about x-axis. That's gotta be clockwise. It's minus 500 times 4 equals to negative 800 times y, and y here is the unknown. All we have to do now is just solve them algebraically. Gonna be 0. Y here should be 4.5 meters. Already have that. Next up is solving my naman, where the summation, where the moment about y-axis is also equal to force resultant times its perpendicular distance, which conveniently lies along the x-axis naman. So just to draw it up now before we continue, should be around here. So we don't know, we already know FR. We just don't know where is it lying relative to its coordinates dito. So this one, this is yung y, and dito yung, we don't know gaano kalayo siya from its respective axis. So we're here trying to determine where it is. This FR here is the representative of all the forces you have here. And we're just trying to determine where is it being applied here on this particular panel. Okay, I hope you understood that. So again, we're just trying to determine where exactly is the resultant force being applied here by, and we're solving its coordinates dito by getting the moments about its x and y axis naman. Okay. And so here naman is x is unknown. So again, FRX times x is equals to the summation of all the forces we got here. The individual forces times their respective perpendicular distance. So in this case, 400 here is going to be 0 since there's no movement. 100 here is going to rotate clockwise relative to y-axis. So that's going to be clockwise there. So negative 100. Yeah, that's clockwise. And then negative 100 times 3. And then 500 naman is counterclockwise. That's 500 times 4. And then 800 times x. Solve it algebraically again. So that's 0. Your x should be around 2.125 meters. Okay. That's about the walkthrough of the problem sets. Let me just upload the correct version for saan ba yun? Woman, I think it's number 9 or is it 16? Yeah, so again, I'm just going to upload the proper answer again in your Canvas. Okay, so thank you for listening in, and already solved already have answers for your problem sets. But as soon as you guys were able to submit it, I'm just going to upload it and have the solution ready. Okay? Thank you so much, and enjoy your holidays, okay? Do take rest.